All right, hello calculus fans. Okay, so today what we're going to do is derivatives of inverse functions, and mainly it's going to be derivatives of inverse trig functions. So let's just kind of start out here. Derivatives of inverse functions. All right, so the first thing I want you to do is I want you to think graphically. All right, if I have y equals 2x, in order to find the inverse function, you guys should know how to do that already. Remember, you just switch x and y. So we're going to get x equals 2y. Solve for y, get y equals 1/2 x. Okay? And notice the slopes of the original function and this function. They are the reciprocal. Okay? And it's symmetric. If I would actually make a quick sketch of this. So this is y equals 2x and y equals 1/2 x, and then it is symmetric about this line right here, roughly, and symmetric about y equals x. Okay? So just to kind of give you an idea a little bit of symmetry and inverse functions. Okay, so let's actually start with the derivative of arc sine. All right, and of course you guys know we can write this as y equals inverse sine of x, same thing as arc sine. And if you also remember, y is between negative pi over 2 and pi over 2, and that's basically our range. Okay, remember that range chart from back in the day. Okay, so just so we have a little bit more room here, we'll keep going here. But basically, if I do d by dx, or I start out with y equals inverse sine of x. Okay, and then I take the derivative of both sides. So I get, if I do d by dx of y, I wind up getting, if you guys remember, it's d by dy of y, which is 1 times dy dx. So I just get dy dx is equal to d by dx of the inverse sine of x. Okay, and that's pretty important here because we're going to substitute that later when we're going to solve for dy dx, and then you can just substitute for dy dx the derivative d by dx of inverse sine of x. All right. So let's actually do the inverse. I can now take this guy right here, and I can rewrite this as x equals sine of y. That's the same thing as y equals inverse sine of x, right? And then I can take the derivative of that. So d by dx of that is going to be 1 is equal to d by dx of sine of y is cosine of y dy dx. Okay, this is again just taking the derivative implicitly, and then we're going to solve for dy dx. So dy dx equals 1 over cosine of y. All right, so now really what I want underneath here is I want something in terms of x. Okay, or I actually want something that I can substitute. I shouldn't say in terms of x. I want something where I can substitute this guy right here into that. So what I'm going to do is I'm going to use one of my identities from back in the day, and it's just going to be cosine squared of y equals 1 minus sine squared of y. So I take the square root of both sides, I get cosine of y equals square root of 1 minus sine squared of y. So I can write this as, let me give a little more room here, dy dx is equal to 1 over the square root of 1 minus sine squared of y. Okay, now I can substitute that in, right into there. So dy dx equals 1 over the square root of 1 minus, and sine of y is x. So 1 minus x squared. That's pretty friendly. Okay, and now what I can do is, remember when I first solved this right here, this guy right here, up here in the upper left, dy dx is the derivative of dy dx of inverse sine of y. I can now substitute that in. I can say d by dx of inverse sine of x equals 1 over the square root of 1 minus x squared. Okay, that's pretty much what the derivative is. I'm going to write this in terms of u because I want to be able to apply the chain rule. So this is my final answer here, actually. D by dx of the inverse sine of u is 1 over the square root of 1 minus u squared du dx. That's the only thing I did here is this is basically the chain rule. So when I have something instead of sine of u, inverse sine of u, I might have inverse sine of 2u. Then you got to take the derivative of 2u, which is 2, and get your answer. Okay. There's only one restriction that I have to give for this, so I'm gonna box this first here. This is really important. And there's only one restriction: is the absolute value of u has to be less than 1. All right, because if it's not less than 1, if it's greater than 1, you get a negative radical, and you can't have that. So that's your first derivative, inverse trig derivative. All right. So let's derive arctangent, derivative of arctangent. So derivative of arctangent. So it's going to be the same thing. Y equals inverse tangent of x. And I can take the derivative of both sides, d by dx of both, and I get dy dx is equal to d by dx of inverse tangent of x. So again, I'm doing this so I can, once I solve for dy dx for the next equation, I can just substitute that d by dx inverse tan of x for dy dx. All right, so let's write this out as we did before. Tangent of y equals x, which is exactly the same thing as y equals inverse tangent of x. Okay, then I'm going to take the derivative of both sides. And I get dy dx of secant squared of y. Right, because derivative of tangent of y is secant squared of y, and then of course dy dx, and the derivative of x is 1. So dy dx equals 1 over secant squared of x. So once again, math fans, I'm going to try and get something to substitute that in there, and it's using our identities. Okay, basically our Pythagorean identities. So here's another one of your identities. Secant squared of y is equal to tangent squared of y plus 1. So I'm going to substitute that in. Dy dx equals 1 over tangent squared of y plus 1. Now I can take that guy right there, the tangent of y, and plug it in. So dy dx is equal to 1 over tangent of y is x, so it's x squared plus 1. Okay, pretty nice. And then as I write this dy dx, I can substitute that in. So d by dx of the inverse tangent of x equals 1 over x squared plus 1. No restrictions for this, right? Because, you know, if x is negative or 0, it's still going to be positive underneath. There's no radical. We're good to go. The only thing I'm going to write is d by dx of inverse tangent of u is going to be 1 over u squared plus 1 times du dx, using the chain rule again. Alright, that's that one. And let's do our last one here, which is going to be pretty much the same. Okay, and so this is the derivative of arc secant. Okay, so y equals inverse secant of x. Take the derivative of both sides. Once again, we get dy dx equals d by dx of inverse secant of x. And as I said before, that's so we can substitute that back in later. And so let's write out, instead of writing y equals inverse secant of x, we're going to do secant of y equals x. Then we do d by dx of that. So the derivative of secant y is, first of all, it's dy dx of secant x, or secant y, tangent y. And derivative d by dx of x is just 1. Alright, so we're going to solve for dy dx. And we get 1 over secant of y tangent of y. Alright, so now we got to do a couple of substitutions. One is we already have, here's secant y, guys, so we can substitute that in. So it's dy dx is equal to 1 over, and that's x. That's pretty sweet. And then what about this tangent of y? Well, again, one of our Pythagorean identities, tangent squared of y equals secant squared of y minus 1. Take the square root of both sides, so we get tangent of y equals square root of secant squared of y minus 1. And again, here's the secant of y. So I can take that secant of y and substitute that baby right into there. So I really get tangent of y is equal to the square root of x squared minus 1. That's our final thing. So I'm taking that guy and substituting that into there. So I have, of course, 1 over x, and then this is going to be square root of x squared minus 1. Okay? And then I can substitute, of course, right here as before. Substitute that in. So it's d by dx of inverse secant of x is equal to 1 over x square root of x squared minus 1. Okay, and the only additional thing I need to do here is, if I make a piecewise function, when x is greater than 1, you have a positive slope for this problem. Okay, when x is less than negative 1, you have a negative slope. So the only thing I need to do with this problem is just adjust this a little bit and put the absolute value around that x. Okay, just to compensate. It's kind of like when we did absolute value in a piecewise. It's kind of the same idea. So my final answer to this problem is d by dx of inverse secant of u is equal to 1 over absolute value of u times the square root of u squared minus 1 du dx, using the chain rule. Okay, that's it. And there's one restriction here. Notice u squared minus 1 it has to be absolute value of u is got to be greater than 1. Okay, so that is the derivative now of arc sine, arc tangent, and arc secant. Okay, we have 3 more to go. Brutal, brutal. Let's talk about the derivative of cosine, inverse cosine. Well, okay, do we really have 3 to go? Not really. This is the deal. If I make a quick sketch here, and I make a 30, 60, 90 triangle. Okay, so this is going to be 1 and 2 and root 3. Okay, I want you guys to remember our cofunctions. Okay, that's actually really, really important. And if I do inverse cosine of 1/2, if you guys remember, the inverse cosine of 1/2 is the same thing as 90 minus inverse sine of 1/2. Okay? And if you want to test this out, remember the cosine of what is 1/2, and it's going to be 60 degrees. And the sine of what is 1/2? That's going to be 30 degrees. So 60 equals 60. All right. So basically what you do is it's 90 minus that angle. Because remember, these represent an angle. That represents a theta, and that represents theta. Of course, a different theta, because we're talking about the same ratio, but a different theta. Inverse cosine of 1/2, I said, is 60. So we're here, and so my ratio for the ratios are the same. Because remember, cosine is adjacent over hypotenuse, so 1/2. And then if I go over to the other angle here, the 30, opposite over adjacent, so 1/2. The ratios are the same. So if you know this guy right here, that they're cofunctions, it's just 90 minus that angle equals the cosine. I can kind of put this together. I can say inverse cosine of x, generically then, equals, and we'll do this in terms of pi over 2 minus inverse sine of x, right? Because that's exactly what I did here. X represents the same ratio. Okay, and it's just a difference of 90 minus that value. All right, this is really key here, guys, because this is the deal. I'm going to do d by dx of that. So d by dx of inverse cosine of x equals d by dx of pi over 2 minus d by dx of inverse sine of x. So we're going to leave that alone. D by dx of inverse cosine of x. And what is it? And if you guys remember, d by dx of pi over 2, it's a constant, so it's 0. So really, we just have this. So the inverse derivative of the inverse cosine of x is just the negative, or the opposite of the derivative of inverse sine of x. That's actually really, really nice, because now I can just say d by dx of inverse cosine. And I'm going to actually start out with a u here, just to simplify it a little faster. It's just negative 1 over the square root of 1 minus u squared du dx. And it's got the same restriction. Absolute value u is less than 1. Okay, that's it. That's pretty nice. So it's just a negative of that. Okay, and it's the same thing with tangent and cotangent, and secant and cosecant. Okay, so sine, cosine, these are all the same. Okay, so we actually spent a little bit of time doing these guys right here, and these guys are just going to be a negative of those. That's all they are. Okay, so that one's for cosine. Let's just do cotangent real quickly. Then it's just going to be d by dx of inverse cotangent of u equals negative 1 over u squared plus 1 du dx. And same thing, d by dx of inverse cosecant of x equals negative 1 over u square root of u squared minus 1 du dx. In this case, again, remember, absolute value has to be greater than 1. Okay, so now we have all 6 of them, and these were really easy because it's just a negative. And just a way to remember it, again, sine and tangent and secant, that's positive, and the negatives are the cos. Co, and co. So cosine, cotangent, and cosecant, or cosecant. Okay? That's just an easy way to kind of remember these. All right, so let's do a couple examples with these now. And it's basically just, substituting into one of those three equations, obviously if it's positive or negative, and using the chain rule. That's pretty much what it is. All right, so let's start out with y is equal to inverse sine of 3x squared. All right, so we're going to do take the derivative. So d by dx. So we get dy dx is equal to, and what we're going to do is we're going to take that 3x squared and we're going to put it in the equation. So it's going to be 1 over the square root of 1 minus, and remember it's u squared. In this case here, u is equal to 3x squared. So it's 1 minus 3x squared, and that's squared because it's 1 minus u squared. And then it's du dx, which is just going to be times 6x. Okay, that's just what that is. Okay, and then we just simplify it. So dy dx is equal to 6x over 1 minus, and we just multiply that out, 9x to the 4th. All right, and we're done. That was pretty easy. That was pretty mellow. Sometimes you're going to have to simplify it even more. Okay, but just remember, I always want one fraction, and I don't want any negative exponents. Okay, so let's try another example here. Y is equal to inverse cosine of 2 over x. All right, so same idea. It's going to be dy dx is equal to negative 1 over square root of 1 minus u, which is 2 over x squared. And then it's times, using the chain rule. So it's bottom times the root of the top, which is 0, minus the top times the derivative of the bottom, so negative 2 all over the bottom squared. All right? And we need to simplify quite a bit here. Can't have this negative or the radical underneath in a fraction also. So we're going to have negative 1 over square root of 1 minus 4 over x squared times negative 2 over x squared. And we're going to get a common denominator here. So we get, we can put things together. Negative 1 times negative 2, that's just going to be 2. And it's going to be x squared times the square root of x squared minus 4 over x squared, right? Common denominator, there's x squared. Okay, so we have 2 over x squared times the square root of x squared minus 4, and the square root of x squared is x. And so that cancels with that, and we wind up having 2 over x square root of x squared minus 4. Now the deal is, you notice how that was originally an x squared? That's always going to be positive. That number can't be negative just because of that x squared originally there. So what I can do is put absolute value around there. And I want to show you something too, that sometimes it makes it easier if you switch things around a little bit, and this is what I mean. I could have also rewritten this as y is equal to inverse secant of x over 2. Right? You can take the reciprocal of that, okay, because it's just a ratio, and so the reciprocal, secant is the reciprocal of cosine, and then I can use secant instead. So let's just watch. Dy dx is equal to 1 over absolute value of x over 2 times the square root of x over 2 squared minus 1 times the derivative of x over 2. Now the nice thing about that is the derivative of x over 2 is just 1/2. That makes it a little bit easier. Okay, so dy dx is equal to, well, that 2 in the bottom, I can just multiply. I can actually cancel these out, right? Because that's really, if I put this all over a fraction here, oops, all over that fraction, isn't that just a 2 over 1 here? And that's those two, the 2's cancel out. So I get 1 over absolute value of x times the square root of x squared over 4. And let's get a common denominator again. So dy dx equals 1 over absolute value of x times the square root of x squared minus 4 over 4. And then I can take the square root of 4, which is 2. Absolute value of x times the square root of x squared minus 4. And this is really all over 2. So the 2 can go to the top now, right? It's just like division. So your final answer is dy dx equals 2 over absolute value of x square root of x squared minus 4, which is exactly that. Okay, so sometimes it's easier to flip it around, especially when you're using the chain rule, because then you don't have to deal with as much. This is this first one using the quotient rule. I had to do a little bit more work. This one is just power rule. Derivative, like I said, is of 1/2 x is just 1/2. Okay, so it's just, that makes it a little bit easier. Okay, let's try another one here. Y is equal to inverse secant of 2x plus 5, and I'm going to tell you that x is greater than 1. So, pretty easy. dy dx is equal to 1 over absolute value of 2x plus 5 times, right, that's u, right? So it's 1 over absolute value of u, and then it's u squared, or 2x plus 5 squared minus 1, and then it's times du, or du dx, so it's just going to be times 2. The derivative of 2x plus 5 is just 2. Alright, so let's simplify this a little bit. So it's going to be 2 over absolute value of 2x plus 5. And let's simplify inside here. You get 4x squared plus 10x, or 10x, so plus 20x, plus 25 minus 1, so plus 24. Okay, so the deal is I can factor out a 4 here. So it's equal to 2 over 2x plus 5 times the square root of 4 parentheses x squared plus 5x plus 6. And then the square root of 4 is 2, so it's 2 over 2x plus 5 times 2 square root of x squared plus 5x plus 6. And the 2's cancel, so my final answer, dy dx, is equal to 1 over 2x plus 5 times the square root of x squared plus 5x plus 6. Okay, and that's the answer. Now, you're like, well, wait a second, what happened to the absolute value? Or, we still have absolute value in here, so we're almost done. I should have said this too also here. I can rewrite this like that. And you're like, wait a second here. You can't just get rid of the absolute value. But why can't I get rid of the absolute value? Because of this guy right there. X has to be greater than 1, so that part has to be positive, so it's just 2x plus 5. Very easy. Okay? So kind of look, sometimes you're given a restriction like that, and that helps out, lets you eliminate that absolute value. Alright, one more example, math fans. Y is equal to inverse cotangent of the square root of x minus 1. So dy dx is equal to negative 1 over 1 plus u squared. And then it's du dx. So remember, this is x minus 1 to the 1/2 power. So the derivative is 1/2 times x minus 1 to the negative 1/2. And then you take the derivative of the inside of that too. So that was like a 2x minus 1, then you would say times another 2. Okay, so you kind of have to do the chain rule. Alright, so let's simplify this. Square root of x minus 1 squared is just x minus 1. So it's 1 plus x minus 1 times 1/2. And this is actually on the bottom. So it's x minus 1. Right? So we have 1 on top. That cancels, and we have x, actually 2x, square root of x minus 1. Okay, and actually we lost our negative here, so that stays with that, and that's our final answer. Okay, so it's negative 1 over 2x square root of x minus 1. Okay, but the key here is watch your algebra. Okay, that's actually pretty significant. Okay, it's probably the biggest mistake. Calculus is really not that bad. It's the algebra. So remember, I would prefer one fraction if possible, and no negative exponents. All right, that's it, math fans. Have a nice day. Goodbye.